paper, layering on it, some on the wall.
Also, pull out the worksheet that I gave you guys. You picked up one of them yesterday. It's got a big chart on it that looks like this. These two big tables. Right, so from the scientist experiments and from your background knowledge, you know that atoms are not just big blobs. We know that they have little particles on the inside. So we call those subatomic, so lower, smaller than atomic size. And at that point, we've said, oh, atoms are divisible. Atoms can be just subdivided into their subatomic particles. Name off the 3 subatomic particles. I'll start. Protons, neutrons, and electrons, right? So we know those all have distinct characteristics, and those distinct characteristics are generally what we speak of as their charge, like what charge they carry. So as it falls, we're going to go in this order. Protons are what charged? What's their overall charge? Positively charged, right? So they're positively charged. But their characteristic not only is the fact they're positively charged, but generally they are paired with electrons to make an overall neutral molecule. So what must be the charge of electrons? Negative. So if they are negatively charged, and I have equal number of positives and equal number of negatives in one atom, overall the charge of that atom is neutral, so no charge. That is generally what we talk about. Is that if I say a potassium atom or a carbon atom or a hydrogen atom, when I say that as an atom, that means that they have equal numbers of protons and neutrons. So if you ever use the word atom, to me and now you, we should understand that that atom contains equal protons and electrons. Remember, my abbreviations are P plus and E minus for that. So that's the characteristics of a specific atom. So everybody, oh, you also have a periodic table somewhere nearby. Okay, pull out your periodic table. Find bismuth for me. BI, bismuth. Okay, point to it when you find it, so I know you got me here. All right, it's in the what general region. So post-transition metals, so on the right-hand side, 83, right? Right. When I say number 83, I'm actually saying what would you call that number? Say again? The atomic number, right? So atomic number 83 is bismuth. That's its identity. But there's something inside of it that we actually characterize more as its identity. It's actually the number of protons. So the number of protons controls the identity of the atom because it designates its atomic number. So for example, bismuth is atomic number 83, and that means it has 83 protons. And since in this case I'm talking about an atom of bismuth, what also does it have 83 of? Electrons. Neutrons we've not spoken of yet, so I'm going to hold off on that. So potassium, okay, what is the atomic number of potassium? Good, 19. No one said like phosphorus or other number. Right, so K is potassium, so it's 19 protons because that's the atomic number. And if it's an atom of potassium, it also has 19 electrons. That's because they will be considered neutral overall. Okay, so if I'm not a neutral atom, so non-neutral, I'm called not an atom, I'm called an ion. So you've heard the term ion before, but just remember now that they will have a charge. So what I mean by that is that we will indicate a plus charge or a minus charge or a plus 2 or plus 3 or minus 1 or minus 2, minus 3 on the symbol. So a cation has a positive overall charge and an anion has a negative overall charge. So cats, what do they have on their hands? Paws. Cats are positive. I try, guys. Cats are positive. Okay. And then anion just sounds negative. Anion. It just sounds negative. Or you can think of the T as the positive, and there's no T, so it's a negative. You basically have to memorize that a cation is a positively charged ion and an anion is a negatively charged ion. Okay, so there's only one way that you can achieve a charged particle. You can only remove or exchange one type of subatomic. So protons, and I didn't draw my picture over here. So generally we draw the protons inside of this, which we call the nucleus. So in the nucleus we have protons, protons, protons. Okay, so I drew 3 protons. So what atom is this? Lithium. Okay, so 3 protons is lithium. So the protons are really well hidden away and tucked inside the nucleus. Outside we have the electron cloud, where guess who lives? Electrons, right? So it's very, very difficult to pluck a proton out of the nucleus. It's well hidden away. It's very, very secure. So if I'm forming an ion, I'm never, ever, 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 ever going to change protons. Because once I change proton, let's say I add another proton here, I don't have lithium anymore. Who do I have? Beryllium. So I've actually changed the identity of the atom. So I never want to do that because you can see, for example, here I'm going from magnesium neutral, no charge, to magnesium 2 plus. So I have to exchange one type of subatomic particle, which is not the proton. So who's more accessible? Electrons, right? So the electrons are out here. Okay, so they're just hanging. It's really easy to take one away or to add one in. That's super easy because it's on the peripheral of the atom. So in forming ions, you only change electrons. That is the only subatomic particle you can change. So that's going to be something we'll keep referring to. So if I was magnesium, I would initially, how many protons do I have? Look at magnesium. How many protons? 12, because that's its atomic number, right? All right, if it's neutral, because you can see there's no charge. How many electrons? 12, because it's equal. Okay, so in this case, what has not changed? Protons, so it's still 12 protons. But what has changed? Electrons. Okay, so for even 12 and 12, right? 12 protons, 12 electrons. But I overall get a 2 plus charge. Can I gain electrons? Not sure how that's playing or where it's playing from. The cell phone from someplace. It's random, guys. Just Pandora says thing. That's the first time that's actually ever happened. Okay. It was a good song, but moving on. Okay, 12 protons, 12 electrons. Can I gain 2 electrons and make a positive charge? No. No. Gaining, you think, oh, gaining is a positive thing. No. Negatives, or electrons carry negative charges. So if I gain 2 electrons, I'm getting 2 more negatives, so what would be my charge? -2. So this occurred by the loss of 2 electrons, because now I'm deficient by 2 negative charges, so that deficiency of 2 negatives makes me overall positive. So now I have how many electrons? 10. And you can see the difference there. I have 10 negatives and 12 positives, so overall I have a positive 2 charge. So that's something sometimes you have to think about before you start rationalizing. Okay. So Anna, describe protons and electrons for these 2 here. Write it on your paper someplace. All right, Corbin, how many protons do I have in oxygen?
8.
8. So it's atomic number 8. So we have 8 protons. How many electrons in our neutral species here? 8. Okay. Oops. 8 protons and 8 electrons. All right, Cole. Well, how many protons do I have in this one? 8, because I never change protons, right? Everybody else, how many electrons do I have? 10, because I have gained negative charge, which gives me the negative charge, and plus, obviously, we have an anion, so it has to have negatives, so we must make it more negative by adding electrons. All right, so that's how we make an ion. It's a non-neutral species. And then lastly, the neutrons are generally not going to change. Where do the neutrons live in this atom? In the nucleus. So I'm just drawing little zeros, okay, which because they have, overall, neutrons have no charge. Good. So they're not contributing to the positive or negative nature of the overall atom's charge, which is why we do not talk about them in reference to ionic charges. So if I have, what's the molar, or what's the average mass of sodium? Average mass of sodium. 22.99, right? But I'm going to round that to 23 to have a mass, like of a full integer, so we'll talk about why that is in a second. But if I have a mass of 23, that's made up of two subatomics, protons and neutrons. Electrons, you guys read this on your table and reading guide forward. Do you guys remember how big electrons were, how massive they were?
It was like
1 over... Yeah, so like essentially massless, right? So 1 over almost 2,000. So 1/2,000th of a gram. It's teeny tiny. So we know that they have mass because they're matter, right? They matter. But we essentially say they have no mass because they're so negligible. So the sodium's mass of 23 is made up of only the proton mass and the neutron mass. How many protons does sodium have? 11. So how many neutrons should it have? 12 to overall give us 23. Okay? Or 23 is our mass. So that's one example. Or you could take the mass number of 23, subtract the atomic number of 11 to get the neutrons of 12. Okay? Right. Give me a thumbs up if you're good on at least baby steps here. All right, and you've heard a lot of this before. Who kind of, this is not new. Okay. So some people's earth science classes or 8th grade science might give more information than others. All right, this is on the paper I provided, right, to the top. So keywords so far, atoms, ions, and now isotopes. Isotopes are not really anything special. Literally every atom in the world is an isotope. Everything. But the way we identify like couples of isotopes or multiple isotopes is that they all have the same number of protons, meaning they're all the same type of element, except I can have isotopes of carbon. So for example, I can have isotope carbon 12, carbon 13, and carbon 14. Who's heard of some of these? Okay, we've talked about that with radioactive dating for like 10 years of our life. So this 12, 13, and 14 thing are just different masses. But since they're all carbon, they have one thing in common. What is it? Their atomic number. So all of these carbons have what is their atomic number? 6. So all these carbons have 6 protons. But all of these carbons, in this case, mass of 12, mass of 13, mass of 14, different masses are caused by a different number of neutrons. So this carbon has how many neutrons?
6.
And this one has 7. And then this one has 8. But they're all simply carbon. If they just are called isotopes of carbon because they have different number of neutrons, which gives them a slightly different mass. But literally everything in the world is an isotope. It's just not necessarily isotopes of each other because they're all different atoms. So in terms of notating specific information about isotope, there's this method and then there's this method down here. So this is called the A to Z notation. So if I ever ask for you to write the A to Z notation, this is how you write it. So the A number, let me write, well, I'll write here. This is the A number, it's the top number, and then, I can't see that anymore. And then the bottom number is called the Z number. All right, so the A number is the top number, the bottom number is the Z number. It goes in alpha order. The Z number is the atomic number, also known as the number of, say again? Protons. The mass, or the A number, which is the top one, is the mass number, which is actually the summation of protons and neutrons. Okay, so in terms of looking at the symbol is going to be the letter in the middle. And then lastly, if you have a charge, it's going to be on the upper right-hand side. Okay, what is the only subatomic particle that changes to allow us to have a charge? Electrons. Okay, so essentially everything indicates something different. You basically have the total of protons and neutrons. You have just protons. and you say, oh, did electrons change? Let me indicate that here. So this gives you a whole lot of information about a select number of isotopes. This one gives you less information because really you have the periodic table like at all times, so there's no need for me to tell you the proton number because you could look on the periodic table. Notice that uranium-238 doesn't tell you the proton numbers. What are the protons in uranium? Uranium's in the actinide series. 92, right? So I don't have to tell you that, right? So uranium, you could indicate this differently by putting 92. This right here is the mass, and now on your periodic table, what does it say for uranium's mass? 238? Oh, I was thinking it was slightly different. Okay, so 238 is the average, the most abundant form of uranium, which is why it's also really close to the average mass you have there. So I can, instead of putting dash 238, I can put 238 up here. Does this indicate any charge, positive or negative? No, so that is not a negative, that is a dash. Okay, so I will not put a charge up here. So in this case, how many protons do I have? 92 protons. How many electrons do I have? 92, because there's been no change of charge. And how many neutrons do I have? Math, come on, you can do that. 146, thank you. It's basically a subtract 100, add 8 back, right? So it's like, yeah, you can do that. So in this case, you're doing 238 minus 92 to give us 146. So it's actually like a little math problem in itself. Okay, so that's how you will indicate information on an A to Z notation, or this other one's called a mass notation. All right, now we're looking at the paper in front of you, which is going to be a big chart. You see this chart? I'm going to do maybe 4 right now, and then let you guys ask me questions from there, because after you get the hang of it, it's quite easy. All right, so some of these boxes will not apply, especially if we don't have, or if we have different information. So we see H here, right? I do not indicate a specific isotope because I'm not telling you the mass. So we have to use periodic table, okay? Everybody tell me the atomic number of hydrogen? 1. Immediately, you know, that equals what? Protons. Okay, so 1 atomic number, 1 for the proton number. Do you see a charge here? No, so what else do you know? 1 electron, because that would be equal, so it gives us a 0 charge. Okay, from this symbol we know nothing else. Okay, but so look at the periodic table, and what other information does it say about hydrogen? Okay, so it tells us the average mass is what? Okay, so 1.01, or some of them might be even like 1.008. But this is our mass, average mass of hydrogen. Okay, hydrogen comes in many forms: hydrogen 1, hydrogen 2, hydrogen 3. That's pretty much it. So the average represents not actually a specific atom. There is no atom of hydrogen that actually weighs 1.01. But there's a hydrogen that weighs 1, 2, and 3. So we have to basically take this and round it to the closest integer, because you can't have like 0.01 of a neutron. You can't have halvesies of a neutron. Okay. So what's my closest? 1. So the average mass close would be 1. Okay. So we're putting atomic mass, because there is no mass number indicated here, so there's no dash number. So I don't need this block here. So the atomic mass is 1, and so that gives me how many neutrons in my atom? 0. Good, because mass is equal to protons plus neutrons. So 1 plus 0 is equal to 1. All right, skip down to the third example, so H-2. So hydrogen 2. So what do we know? Atomic number is 1. Also, proton number is 1. Is it charged? No, so 1 what? 1 electron. Okay, so those are the easy ones to fill out first. But we see a -2, so what do we know? The mass number. So basically, if you're pulling stuff off the PTOE, periodic table, you're going to call that atomic mass, because that's the average atomic mass that you rounded straight from the periodic table. If you have a dash or a mass number indicated in the isotope notation, you put it in the mass number notation. So I don't need this one over here. Really, you need one or the other here. Okay, how many neutrons? 1, good. So mass number is 2 equals protons plus neutrons. All right, I want you guys to attempt. Go from the top to the bottom. If it just says plus or just minus, it means +1 or -1. Only because it just gets messy if you put more numbers. So that would be +1 if you're concerned about what that positive charge is. Compare with the person behind you if you finish. All right, and then the couple that I do want to ask you about, and give me a thumbs up if you got the electrons, because that's really the only part that most people find challenging. Everybody tell me oxygen's electrons. 10. So they started off, so oxygen neutral starts off with how many electrons? 8, but then we see a 2 negative charge, so we add 2 more negative things, which are those 2 electrons. That's 10. The other ion, calcium, starts off with 20 protons. It starts off with 20 electrons, but now it's a 2+ charge. So what happened to electrons? We subtracted 2 away. So we took away 2 negative charges to make it a positive overall. So we went from 20 to 18. Phosphorus starts off with 15 protons, 15 electrons, but now it's got a -3 charge, so you have more or less electrons. More by 3, which is going from 15 to 18. So those were the ones I knew that you would need to like just have a moment to think about before I gave you stuff to check, okay? So check up here for yourself for like another minute here. Make sure you're good. And then will this group give her other laptops, devices with me on? And then last year, this helps if I stagger a little bit. And then go to my website if you would, guys. So we're not quite done with notes, but I'm going to have you guys practice for a little bit on this concept before I move on to atomic mass in about 10 minutes. Okay? So when you go to my website, go to homework. I'll show you where you're going. When you're just getting logged on. Alright, so some of you guys are getting ahead, but just make sure you're logging on and I'll show you where you're going and then you can move on, okay? So under Friday's homework, I just put like a classwork link here. It's easy enough for you guys to find. It's a build an atom exercise, just so you understand just a little bit more about these relationships. We won't practice this for very long, but when you click on build an atom and you go to this, you'll come up with this document. And it tells you can either go to my webpage and see it, which is just embedded, it's small, or you can go to the PhET source itself, which is where this came from. Either one of those will work for you, it should. As you scroll down, I put this in yellow so that you can see that you will do a little quick sketch of some diagrams, which is just like 2 circles and a square. And it tells you exactly what to do. So it says to click the atom link for build an atom, so see the symbol, mass number, and net charge, which is the overall charge. Net charge is the overall charge. It tells you what to do with the subatomics. So let's play and then draw these diagrams for maybe 10 or 15 minutes. You can work the person next to you, okay? We'll get as far as we can, and then we'll talk about some of these conclusion questions. Yeah? Sometimes it does that. It depends on if you've logged in on that. Yeah? So, that or try to log in like 17 times in your year. Look at all these IT specialists in here. Alright, so you know you're going to homework, classwork, build an atom, and then going here. My goal is for you to get to the critical thinking questions. So, spells are on the board. Alright, so I'm going to give you guys probably 20 or 25 minutes to work through this process in the lab before I teach you about average atomic mass. So it's inquiry, you're discovering, you're talking, you're discussing what this means, okay? So you have a bag of beanium, which is the element beanium. So you have a bag of beans, and there are 4 isotopes of beanium. There's lima beanium, pentobeanium, black beanium, and another beanium that's in the bag. So you are dividing your 4 isotopes into weigh boats, just so you can kind of keep them together. After that, you're going to measure and record the total mass of the type of bean and so forth. So essentially, you're going to have 4 isotopes. You're going to count those isotopes. You're going to mass those isotopes, and you're overall going to figure out the average atomic mass of the element beanium. Okay? So the instructions are in your lab, or there they are, kidney beanium. Okay? You are going to have to draw this data table. Okay? Just it will take a minute in your lab. Decide on percent occurrence, which is just, it tells you how to calculate, but it's just based on percent. Like if I said, okay, figure out the number of boys in this class, how would you figure out, percent of boys in this class, how would you do that? Count the entire class, okay, count the entire bag of beans, and count the boys, which is the ratio, right? And then how would you calculate? Right, so in terms of percent of anything at all, doesn't matter what you're doing, you're looking for a thing you want, which is, if I said percent boys, you look for a number of boys, or lima beanium, right, that thing you want over the total, times 100 will always give you percent, okay, so that's our general for percent. Alright, so I have enough activities out for you guys to be in groups of 2 or 3, okay, you need to share the lab notebook though, because I'll leave this up for you, but you'll notice that you still probably don't look at the lab notebook. Groups of 2 or 3, I think we can make this work. Let's go. Lab notebook, class. Full lab notebook and share. Full lab notebook and share. Look for a scale and a bag of beans. That's do not mix my beaniums up with another group, or I will not give you your green. All right, come on. You need to have this point. Bring everything with you. All right, so if you're in the front, listen up. If you're in the back, listen up. All right, so the process that you guys went about to find your average atomic mass was you first segregated the beans, and then you did what? You counted them. And then you got their total mass. Okay, that was just simply because not all of them were exactly identical, but in real life, atoms are supposedly that specific type is identical to itself. Okay, so then after you got that far, what was next? You found the average mass of one specific being. So it was a weird, obscure number, but you found the average mass. And then percent occurrence. That is the same phrase as relative abundance. Okay, so you need to now know that both of those mean the same thing. So write this someplace in your notes. Relative abundance simply means what? Percent, right? Percent occurrence is a fancy way of saying it. It just means percent. So after you found your percent, you kind of knew the breakdown of like how many pinto beans, lima beans, etc., kidney beans that you had of this overall sample. So that is analogous to me saying, okay, well, I have a sample of, let me go actually here. I have a sample of chlorine. I have all the chlorine in the world. And of all the chlorine in the world, I've broken it down into the two isotopes of chlorine that exist, chlorine 35 and chlorine 37. Well, you did yours based on the beans. Okay, pay attention up here for me. If you're in the middle of your lab sheet, you're fine. Just hold on, okay? So we broke it down, and then we found the percent. All right, after you found the percent abundance, how did you overall find the average atomic mass of being? Some of you guys made this part. Go for it, Ryan.
So we
Yes. So after you found your percent abundance and the average mass of one of your beans, of all four beans, sorry, how did you find the overall average atomic mass?
We multiplied. Well, first we wrote them in percent, so we divided it by 100.
So you got the decimal form of the percent.
And then we multiplied it by the average mass.
And then?
We added all the average mass.
That's it. You multiply the percent by the average mass, you add them up. Okay, that is not like a normal average in math class. Normally, you add everything together and you divide it by the things that you added together, right? So if you added 4 beans together, you'd have divided by 4 beans, right? But was everything 25%, 25%, 25%, 25%? No. So since we don't have an equal amount of all these isotopes in the world, we never, ever, ever, ever divide by the total at the number of things you add together at the end. We never, ever do that. We pre-think how the percent is proportional, and we actually use it earlier. So we talk about the percent abundance first, multiply that by the percent abundance, and then we just simply add. We never divide at the end. Okay, so this is just called a weighted average. Like your GPA is a weighted average. That's how you calculate your GPA. So let's do this sample problem, and then we'll finish up with the medium. Okay. So this sample problem, we have 2 isotopes. Write down the 2 isotopes: chlorine 35 and chlorine 37. Okay, so less isotopes than what you were dealing with in the lab, but I've already taken all the isotopes in the world and I've divvied them up and I've counted out chlorine 35 different than chlorine 37, and I know their exact, from their overall mass and dividing by the total number they have, I know their exact weight of 34.968852. You're writing this down with me because you don't have this on your paper anywhere. And you know the exact mass of chlorine 37 is 36.965903. And who's more abundant in the world? Chlorine 37 or 35, right? So chlorine 35 is more abundant. So it was about a 75-25% breakdown, but exactly 75.77% and exactly 24.3 or 23%. So this is kind of the data you collected in your lab, except it's just for real things, and it's for 2 isotopes, not 4. I'm going to scroll down just a little bit. All right, so for us to find the average atomic mass of all the chlorine atoms in the world, we're going to take, and I'll write these steps out for yourself, for you guys. You're going to take the percent and you're going to change it to its decimal form. And what do I mean by that? Divide by 100, because to get to a percent you multiply by 100, but we're going to want to go back to its kind of ratio form, so we're going to divide by 100. All right, so that's step 1. So for chlorine 35, what is its percent as a decimal? Say again?
0.7.
0.7577. And what's chlorine 37% as a decimal? 0.24233. Okay? After we do this, our second step is to simply multiply the decimal percent. I think you can know what I'm saying with that. Decimal percent we just got by the average mass of the isotope. So what was the average mass of chlorine 35? It wasn't actually 35, right? So what was it? 34.9688852. Okay, so this is a multiplication, so I'm taking the percent decimal form, multiplying it by the average mass. I'm going to do that for both of my isotopes. So I'm multiplying by 36.965903. So this is just me multiplying. All right, so I need some human calculators here. I need this group over here and this group here to find the first product, and then you guys find the 37 product. Okay, let's do a quick comparison. So the 35 folks, what is 0.7 blah 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 times 34 point blah blah blah? 26.49 what? 5. I'm sorry, I lost you. Oh, 49. 495. Hold up. Let me catch up. 495. I'm stuck there. Okay. So I know we're going to have some truncation of decimals. 37 people. What's this product? I need somebody to help me out here. 956.
95683.
Okay, hold on. Can't give me more than like 2. Should have 8.956.
8384.
All right, wonderful. So we took the percent and we changed it back to its decimal form. We multiplied that decimal percent thing by the average mass. Now what do? Add the two together and don't do anything after that. So take these two numbers you guys just calculated, add them together. Ready when you are. 35.446. 446. One more.
That's it.
That's all you got? Okay. So when we added it together.
We rounded.
Oh, the first two? Okay, so anybody non-rounded? Is this close? Yeah, okay. So we don't have a unit on here right now, but we need to talk about that unit. This is a real atom. So we have an average atomic mass. That's called an AMU, atomic mass unit. It's a really specific unit, AMU. It's not grams, it's not kilograms, it's AMU. All right, so everybody find chlorine on their periodic table. And every single thing on the periodic table is listed as average atomic mass. First off, is there an atom of chlorine that weighs 35.446? Big or loud and proud. No, there's no single atom of chlorine that actually weighs this. This is an average because I can't put like all the isotopes of carbon and chlorine and phosphorus and whatever on the periodic table. I don't have enough space in that little box. So we've established that we only publish the average. And if I want to give you a specific mass, I say carbon-14. That's a specific isotope. Or chlorine-35. That's a specific isotope with a specific mass. So the average is what goes on the periodic table. So what's the average atomic mass for chlorine on the periodic table? Look how awesome! That rounds up, right? And that would be the average mass of chlorine that we would use for all of our calculations if I didn't give you a specific isotope. Okay, so first step, close your eyes. I give you data, I give you percents, I give you average masses. What do you do? Change percent to decimal, then multiply, then add. That's it. Okay, so let me go to the next one, which is actually what your lab questions were on. This was your first lab question on the bottom, okay? Work with your partner. I'm going to try to hit 1 and 2 for us right now. Write this on your lab sheet. Lab sheet. You don't need to write the question. You need to show all your work. Yeah, show all your work, guys. There's no, you're just using a calculator. I cannot accept that. All right, Bailey, what'd you get for your linear isotopes? The after you multiply the mass by the percent. Give me any of them. Oh, okay. You did all together. Does anybody have a specific one? Yeah, STs.
For the first one, I got 10.12.
10.12. Anybody next one? 0.1201. Okay, the next one. 0.9093. Bailey, what'd you get? So you did it all together, so then you have a final answer. Okay. So percent 90.92. Everybody, 1% back that up 2 places, 7% back that up 2 places. Can I get a final? 147-ish, and you would round that to 2 decimals, so 1.5. Okay. All right, laptop's gonna go up now. Okay. We'll do this last. We'll do the next one maybe Monday. Laptop's up. Hold on to your labs because I know you're not done yet. Keep them in your folder someplace. And I will check your interactions another day. So just keep your Google Doc. Don't delete it. It's on the cloud. It's not taking up much space. It's fine. Laptop's up, please. Oh no. What did I do? Okay.
Yeah,